Yeah.
Okay, so good afternoon, everybody. So I'm pleased to introduce you Ron Kimmel today. So Ron Kimmel is a professor of computer science and electrical and computer engineering at Technion in Israel. And before that, he had his PhD at Technion as well. When at that time I met him, so it was a very long time ago. After that, he had a postdoc in Berkeley and visiting professorship in Stanford as well. And since that time, he has been working on various areas of shape array reconstruction and analysis in computer vision, image processing, deep learning, and big geometric data, and computer graphics as well. So recently, he's been interested in understanding machine learning and his application with medical imaging, computational bariometry, optimization of solvers to problems with a geometric flavor, and application of metric, spectral, Riemannian, and differential geometries. So Ron is IEEE and SIAM Fellow for his contribution to image processing, shape reconstruction, and geometric analysis. And he also founded companies in image processing and image analysis, and also is advisor for several companies. So we are pleased to have him give a talk now. Thank you very much.
So thank you, Laurent. And it's always a pleasure to be hosted in France, in Paris, although I would have preferred to make it physically rather than remotely, so that I would be able to say that there are some familiar faces rather than familiar names. But still, if you have any questions during the talk, that would be my relatively subjective view on this issue of geometry and learning. Please feel free to raise your hand. I will do my best to answer on the fly. So again, my talk has to do with geometry and learning. Learning is this new methodology in computer science by which you train some network to do some classification or understand or enhancement or generation of images. And geometry is this old idea of finding invariants, so finding some parameterization that would be the same no matter what you do to your object. Let me try to zoom into these two threads and try to somehow give my idea of how one could unify them or somehow marry them. Okay, so if we talk about neural networks or deep learning, the first thing that comes in mind is the convolutional neural network. So we have Yann LeCun, Jeff Finton, and Joshua Bengio, who for years said that neural networks is the way to tackle computer vision problems, be it GANs or ImageNet or ConvNet or AlexNet. And the basic idea behind these networks is the fact that within each and every part of the image that we are looking at, there is a convolution. There is the same operation that you apply again to all parts of the image. So you may have different convolutions, and these are these layers that you see over here. And there is some communication between the size and the scale of these convolutions that we are talking about. But at the essence, there is this idea of applying the same machinery, the same operator for each and every part of the image, and therefore you can use this redundancy of ideas, of concepts, in order to optimize a huge network that at the end of the day will tell you if this is a cat or a chair that you are looking at the image. It's not. I mean, today these networks can classify objects in images much better than humans, because they would not just tell you if there is a dog or a cat, but rather almost the DNA of the dog, because it has so much knowledge about the relation between the appearance and the DNA of what you're looking at, something that humans cannot comprehend. So the first thing that I will talk about is some examples of how to use these classical ideas, this convolutional neural network, in order to solve interesting problems. And the first is a project together with the three physicians, Yoav Binnenbaum, Ziv Gil, and Eri Duek, and two of my students, Franz Losberg and Gil Shammai, in which we try to train networks in order to classify some characteristics of breast cancer. And the way we did it is look at what is known as histology. Histology are these slices, thin slices of tissue that you put on a slide and you look through a microscope. And at the end of the day, you determine whether there is cancer or not, what is the grade of the cancer, and then by additional coloring that capture very specific properties, you define what is the specific kind of cancer and how it should be treated. What we try to do is to look at the very first and simple coloring, which is called H&E, or hematoxylin and eosin, and this is something that goes back, I would say, more than 100 years ago. And from this very basic view of the tissue, be able to determine what would be the result of coloring with something which is called immunohistochemistry or even DNA profiling. Can you do that? And in fact, what Gil and the rest of the students did is showing that indeed you can predict some of, in this case, estrogen receptors. You can look at just the H&E and predict what would be the outcome of staining with this immunohistochemistry coloring techniques. Now, the first technique is very simple and easy and fast to color and very cheap. The next one is a little bit more requires more elaborate work, and we have shown that something like that can be done. Now, this whole field of looking at pathological images through using a computer is quite new. In fact, only 4 years ago, the FDA allowed laboratories, pathological laboratories, to use digital images. I mean, these days, digital images are allowed, are actually allowed. You can actually use that in order to analyze images. But this came about only 4 years ago. Now, on top of that, you now introduce a computer, some system, some automatic system that would help the physician, the pathologist, to say what he's looking at and whether there is some pathology in that. And this is quite new. There are some companies that are doing that now, two or three in the US and a couple of them in Israel. And our next challenge is actually pushing this idea forward. And this is something that I have a team of quite a large team that is now working on that. And I hope that you will hear about our results soon. So this is one way of using classical deep learning in order to analyze interesting problems. In this specific case, breast cancer. Okay, another interesting problem is looking at a single image. And from this single image, being able to infer what is the geometry that you're looking at. So this is a result by, again, about four to 3 years ago by Elad Richardson, who actually trained the neural network. And the whole magic here was how to train the network. And for that, what he did, he combined two ideas. One of them is synthesizing geometries by some linear combination of coefficients so that you can generate rough shapes of faces and you relate them to their images. And the other one is using something which is called shape from shading, and this is how the skin reflects the light. So he concatenated two networks one after the other. At the end of the day, he just concatenated these two losses one after the other and was able to reconstruct these shapes that you see over here. And in fact, these results are actually still state of the art. If you look at the balance between stability and accuracy, I think they are, even today, 4 years after they were presented, they are still at the top of the reconstruction algorithm that you have. This is another project by Gil Shammai and Ron Slosberg, two of my students, that synthesize images using GANs, generative adversarial networks. And the idea here was, again, imitating the probability of shapes that you have in nature. And again, what they did for that, they used images in order to, at the end of the day, define whether the shape that you're getting belongs to the population of acceptable faces. And they can actually put expressions on top of these fake synthesized faces that they are generating. This is how it looks like. And if you look if you now feed each and every face into a face recognition system that would give you a point in the plane, and you measure the distances between these points in the plane, and then you put them on a two-dimensional plane, what you see is that with this gun, these points here, each one representing a face, have a distribution which is more or less correlates with the distribution of true faces that you find in population. So if this bunch would be Afro-American, Asian, and Caucasian, then you see that the distribution of the generated faces are actually more or less at the same, acquire the same shape. While if you would have used a linear way of just randomly sampling from some space of linear combinations of, let's call it eigenfaces and synthesizing faces, then what you'd get is something that looks like a Gaussian distribution of faces. So again, this is where generative adversarial network, still everything is classical, everything has this convolution inside, and we were really happy. Yet another example in which convolution plays a role is the following question that we asked together with Alex Bronstein and Amir Livne, and this is, do we actually need geometries or depth in order to recognize faces using a network? And what Amir did, I mean, this is an interesting question. So you have a left image and a right image, and classically what you do is you let a stereo algorithm extract the geometry by correlating points between the left and the right. And then the learning method that should identify faces gets a depth, a geometric profile, as well as one of the images, and tries to correlate it to an identity that, so there is at the end of the day here some signature that is being, that you're trying to correlate with a dictionary of identities. So what Amir did is using an auxiliary network, if you'd like, you can think about it as GAN, but it's not some network that would take the output of the stereo network before there is any 3D that is coming to action, and compare, I mean, and train another network that would find the ground truth of a passport view of the same object. So this is how you make this network at the end of the day that gets to parts of the face invariant to the pose and expression of the object. Again, this is how training was done, and indeed, what Amir was able to show is that if you look at a single image, then, and again, the optimal curve here of false positive compared to false negative would be here at the minimum. He showed that if you just look at a single image, this is the curve of performance that you would get from a recognition system. If you add the texture of one of the faces plus reconstructed depth, you'd get something like that. And if you just use the original stereo before you sort of distort it and noise it with your impression of depth reconstruction and feed it into this network, then what you get is much better recognition rates. So again, in some cases, you don't really need to go, and there is something else clever that he did here, and this is the fact that if you crop the image from different parts of the image, then there would be lens distortion. So what he did is he fed the indices of the part of the image from which this image is being cropped as two other layers, the X and the Y, and this is how it tells the network to, from one side, being relatively compact, I mean, processing a small number of pixels at the end, at the other end, he knows exactly from which part of the frame this face was cropped, and therefore he can compensate for the required distortions. Okay, so back into our geometry. So before I'm getting into geometry, let me just remind you signal processing, the fundamentals of signal processing. In the basics of signal processing, what we have is some function, and you assume this function is given on some bounded domain between 0 and 1, and this is a smooth function, a nice function. And what I'm after, and then again, I know something about the family of functions that I would like to represent. And what I'm searching for is some basis that would allow me to represent this function, say, in as compact as possible way. For example, assume that I'm taking only the first k, the first 10 or 20 functions like that, and the linear combinations of these functions should represent my original function in the best possible way. So B is something that we sometimes refer to as basis if the B's are orthogonal to one another. And the question is, what would be the optimal B's? Now, if the only thing that you know about this F is that its Dirichlet energy is bounded, I mean, in some sense that it is smooth, that the second derivative of this function, if you integrate it, then it is smaller than some constant, then Chaim Brazis, our dear colleague, who now spends a little bit of time with us, showed us that the optimal basis would be nothing but the harmonics. I mean, you just take the second order derivative, and you look for the eigenfunctions, and then what you get are the Fourier, if we assume periodic boundary conditions, or the harmonics in the general sense, okay? And if you take them from the smaller eigenvalue to the largest, I mean the eigenfunctions that correspond from the smallest to the largest, then it's not only that this is the best representation, but this is also the optimal one. So this Fourier is also the optimal basis in which you can represent a function if you truncate these coefficients after a constant number of functions that you're allowed to use. Remember that. In a moment we'll come back to it, okay? Now let me give you probably one of the simplest problem in computer vision, and this is the problem of taking two shapes in the plane and trying to compare to say whether they are the same or not. Assume that you have a piece in a jigsaw puzzle, and you would like to ask whether this piece should fit into a hole that you have in your puzzle. And you just look at both of them, and you pick up the one that would give you the best fit into this hole. And the question is, how should we tackle this problem? I mean, is there a way to define a distance between two curves in the plane? Now, there are various transformations for these two curves in the plane. I mean, if I just rotate and translate them, I would call it a special Euclidean. If I can also flip them, then it would be the Euclidean. If I'm looking at shears and scales that would preserve the area of the objects, which is more general, this is called the equi-affine. If I don't care about the area, this would be affine. If I just blow them up, it would be called scaling, etc., etc. So the question is, how should I deal with this family of transformations of curves in the plane? And if we go back to the very basics of, I would say, finding invariants of curves, differential invariants, then let's just look at the Euclidean transformation. Okay, just consider the special Euclidean transformation. In that case, if I just at each and every point along the curve find the curvature of this point, which is 1 over the radius of the oscillating circle, of the circle that is defined by the limit of taking 3 points and taking the limit to the point, then what I have is a signature of the curve. Okay, this is known for many years, and again, just taking the second order derivative with respect to the Euclidean arc length, and the Euclidean arc length is defined as dx squared plus dy squared, and this defines the square root of the Euclidean arc length. The second acceleration vector is nothing but the curvature vector, and this curvature is the signature of the curve. So if we take this curve in the plane, this shark, and we travel along the boundary of the shark, and we plot the radius of the oscillating circle, then what we get is a signature. And then in order to match one shark to the other, what we need to do is to take this function and shift one with respect to the other. And at the end of the day, we determine if this is the same shark or not. In fact, what Cartan showed us is that if you want to get rid of choosing the initial point, you can take not just the curvature, but rather than the curvature with this, the derivative of the curvature with respect to the arc length, and throw away the arc length, and then you get a signature without dependency on where you start your travel along the boundary of the shape. Okay, so these are Euclidean invariant signatures, and you can use other geometries in order to define different arc lengths. For example, you can think of a scale invariant arc length, and in scale invariant, if you want to, for example, travel between that point and that point, and measure the same number, which would be invariant to how you scale the curve, then what you need to do is basically just measure the change of the velocity vector, the angular change of the velocity vector. And the angular change of the velocity vector is nothing but the absolute value of the curvature times the Euclidean curvature. Okay, so we have defined a new arc length, which is scale invariant. And this arc length is basically a way of capturing the curvature in an interesting way. Okay, the question now is, what do we do with the two stories that I told you? There is one way of taking this function, kappa of s, and presenting it in the most efficient way, which is nothing but taking the Euclidean arc length and taking the eigenfunctions of the second derivative, which would be nothing but the harmonics on the circle. Okay, so I get the Fourier transform, and I get these coefficients, which are the curvature projected, the curvature along the curve projected onto these harmonics. Okay, so this is one way of representing this signature of a planar shape. Very compact one if you assume that your shape is not too is smooth in some sense. Okay, in a Dirichlet sense. Okay, so this is one way of looking at the Fourier, but there is also another way of looking at the Fourier transform. I can take the scale invariant arc length, which define the second order operator, and decompose it into its own eigenfunctions, and then I have a new set of eigenfunctions. Now this new set of eigenfunctions encapsulates inside the curvature. In fact, if I would look at the DC here and the DC there, then the DC in the second one would give me the curvature as part of its definition. Okay, so now the question is, how can I get to these alphas by looking at the interactions between these two harmonics, one of them with the regular arc length and the other one with the scale invariant arc length? And the answer is quite simple. I mean, just take the inner product between the two. So again, this is something that we have seen. And the next one would be just take the inner product with respect to either the Euclidean or the scale invariant arc length, and you get these kind of coefficients, this kind of discrete coefficients that would, at the end of the day, represent your shape. And indeed, what we called it self-functional maps, together with Oshri Halimi, and it's in a sense it is a simplification of a method that I will talk about later, which is called functional maps. By Ostianikov and his colleagues, and I will relate to it later. But what you need to remember for now is that for planar curves, you can translate the curvature as a function to this set of discrete numbers that basically capture the shape of your curve. So you can, instead, rather than comparing this continuous function, you can resort to comparing these discrete numbers of numbers. Okay. Okay. The question is, can we now use the idea of learning, of having this kind of convolutional neural networks in order to, or a function that is doing the same thing again, in order to compute the curvature or some signature of the curve? And the answer, the first answer was yes. And this is a joint work with Gautam Pai and Aaron Wetzler, in which what we did is took as an input a fixed number of points that we sampled about a point along a curve, fed it into a neural network, and we did it using a Siamese architecture. So the same looking curve, rotated, translated, and sampled differently, but with the same point, was fed into the network again. And if the 2 points were the same, we penalized the value, the output value, to be the same. If there were different parts of the curve, and again, you can simulate it in a very simple and easy way, the output value should be different. And in fact, you can train a network, fully connected kind of network that always looks at, I don't know, 15 or 20 points about the point in the center, so that it would produce a number that would be invariant with respect to rotation translations. And in fact, you can generalize it. You can do it also to affine, to equi-affine. And the beauty of the network is that you don't have to think really hard in order to understand what you're doing. You just need to play with the transformations, and then the network should spit out the numbers for you. Now, another beauty is that the network can compensate for discretization error, for quantizations, and the rest of the errors that you can encounter when you are dealing with this kind of transformations. So what we are now doing with PRAIRIE-PSAI is computing the other quantity, which is not less important, which is the arc length. And in fact, it has really promising results. And I hope that in a month we will be able to submit it to some conference. And again, the idea of computing arc length is as, I would say, complicated or trivial as computing the curvature, but you need to be really careful in what you're doing. Okay. Now, with curves, we are really lucky because we have order of the points when we are traveling along the boundary of a shape. So there is, if, for example, we are traveling clockwise or counterclockwise, there is this magic of having order, and therefore there is some signature which has order that you can compute. Surfaces are a little bit more challenging if we think about it. I mean, two-dimensional manifold, curved manifolds, if you have a point here and a point there, nobody will tell you which point comes after which. I mean, there is no relation between them. So what should we do? The idea is to look at surfaces as metric spaces. I mean, look at surfaces as the set of all the geodesic distances between all points to all points. Now, we can also do it for curves. But for curves, if we travel along, say, Euclidean distance along a curve, then the distances, if you look at the distances, you can always embed the distances between points along a closed curve as being equivalent to a circle. So every curve is topologically, or not topologically, but geodesically equivalent to a circle. Why? Because you can just think of the curve as some wire, and you can just inflate the curve so that at the end of the day, without stretching or tearing the curve, and at the end of the day, you will just get a circle, okay? With surfaces, in fact, the intergeodesic distances give you a really concrete definition of the surface up to what we call isometries. So isometries of curves in the plane are useless from the point of view of recognizing what kind of silhouette of a curve we are looking at to begin with. For surfaces, this is the way to go. So let's think for a moment of surfaces as metric spaces, and let's try to see what is going on. So first of all, let's assume that what I would like to do is compute all distances between all points to all points on the surface. So this is my yellow is my surface, and I would like to compute the distances, the geodesic distances on the surface. And for that, we need to solve something which is known as the Iconal Equation. This is we know that the gradient of a distance function is equal to 1. This is something, this is a generic axiom that you should be familiar with. But even if you don't, if you depart from a point in a constant speed, no matter to which direction you go, the gradient is always equal to 1. So you can reverse the order and find the what is known as the viscosity solution to this kind of equation. So it's Jamie Setian, I would say almost more than 2 decades ago, we solved this with something which is called the fast marching method. In fact, I think that Professor PRAIRIE was playing with that at the beginning of his career. And in fact, with Professor Laurent Cohen, we were also using that in order to solve many problems in medical imaging. So the question is how to compute it efficiently. And in fact, together with Moshe Lichtenstein and Gautam Pai, what we showed is that you can take the local update scheme of this fast marching method and train a network to spit out the right solution, the right viscosity solution, again. And you need to be really careful when you're doing this training, but again, you can do that. In fact, you don't need to do it on a regular grid. You can also do it on triangular domains. Now, just a word about triangulated the domains. If for regular grids, we had h is the distance between points here. So this is the grid spacing, if you like. So in 1995, there was a first order accurate scheme that solves the Iconal equation. In 1999, there was a second order approximation, and on grids the story was a little bit more complicated. We had the order of h algorithm, the first order fast marching algorithm, in '98, and only in 2005, after 20 years after the MMP, the Mitchell and Papadimitri algorithm for computing what they called exact on manifolds algorithm was published, Suradsky, his wife, and some other colleagues were able to implement it. So they had an implementation which is second order, in the sense that it was exact on the polyhedron, but if you consider the smooth surface, then this is a second order algorithm. And the question that Moshe had to answer is whether he can use a network to get a second order algorithm with the complexity, with the linear complexity of first order algorithm. So just a comment, the second order algorithm, the complexity was n squared. N is the number of points that you have. So if you think about it, there is some equivalence between having an order of n squared algorithm at second order accuracy and having a linear algorithm that solves in order of h your problem. And the question is, can you actually do something that would benefit from both? And from a practical reason, what Moshe was able to do is that you can do that. I mean, you can use a network in order to get, let me just show you the graphs. So the graph here shows the h as it goes down. And this is a slope in a logarithmic scale that shows how the exact algorithm is improving as you refine your grid. And this is the first order algorithm, the FMM. Okay, so the FMM is the first order inaccuracy algorithm, and the exact as well as ours are second order. Again, ours means the neural network, and the accuracy can be measured accurately if you take a sphere and you triangulate it. And on a sphere, you know exactly what are the distances, what are the geodesic distances between points. Okay, so assume that there is a way of computing all intergeodesic distances between all points to all points, and then the question is, how do we take it in order to compare between two surfaces, S and Q? And the answer is that goes back to Gromov. And what Gromov said is that in order to compare between two metric spaces, you need to ask how can you embed one surface into the other and one and the other into the first, so that the intergeodesic distances are distorted in a minimal way. So in a min-max sense, what you're looking for is for the mapping between all points in S. And again, I'm now taking the liberty of giving you an engineer explanation of the Gromov-Hausdorff distance, throwing away the symmetry. I mean, you need to embed Q into S and S into Q, and then one point of S into Q and one point of Q into S. But let's take only one of them, only one side of the story. So what you'd like to do is take all points from S and find a mapping rho into Q, so that the geodesic distances between point I on S and point J on S would be as close as possible to point I on Q and point J on Q. Okay, so this rho, this continuous rho, which is bijective, is what we are looking for. And this is a problem that was first introduced for that kind of surface matching problem by Facundo Memoli and Guillermo Sapiro. It was 2004. By the way, in the same conference, Jan LeCun was talking about how good convolutional neural networks are. And my take-home message from this conference was that I need to go and work on the Gromov-Hausdorff distance. And in this lecture, I would actually unify the two. So there is some happiness at the end of the story. Okay, so the question is, we have seen that this is the problem that we need to solve. The question is how. And how, I'm going to another famous French philosopher, René Descartes. who actually posed the question is how can algebra describe geometry? How can I translate geometry into equations that I can then solve using the algebraic method? Okay. Let me skip over and assume that you know what is the difference between manifolds and Riemannian manifolds. And let us revisit again this idea of finding this rod, this mapping that would take all the points in S and would map them into the points in Q, so that the distortion would be as small as possible. So that the largest or the average, if you're talking about Gromov-Wasserstein, would be as small as possible. Okay, so the question is, how should we do that? First attempt is the following. And this is something that I did with my student Asi Elad, again, almost 2 decades ago, was the following. Look at all the points in S, at all the intergeodesics as a distribution, okay, as some sampling of some distribution. And then try to use PCA, or it's called multidimensional scaling, in order to translate all these distances into Euclidean ones, okay? So you minimize basically an embedding of all the points in S into R2, 3, or 4 by translating these distances into being Euclidean. Is there any question? No. So the question is, how should we do it? And this is one way to do it. However, here there is a problem. There is a fundamental problem. And the problem is that if I do it for S and I do it for Q, then I can hope to have some similarity. However, the question is, can I always take points from some curved domains and embed them into Euclidean ones without introducing an error? And the answer is no. So if I would take like a sphere, for example, and I would try to embed it into any into Euclidean space of any dimension, the problem is that if I take A, B, and C, they would have to be on a straight line. Why? Because they satisfy the distances between the points, satisfy the triangle inequality as an equality. So A, B, and C should be along the straight line in my embedding into Euclidean space. The same goes for A, C, and D. So I have some problem of embedding points into Euclidean space. And in fact, what Gil Shammai showed is that if you resort to complex spaces, then you can do something about it. Okay, so the next in line was the thesis of Alex and Michael Bronstein. And what we try to do is revisit the Gromov-Hausdorff that Sapiro and Emily introduced and do something about it. And what we did is solving this problem of taking the intergeodesics on S and the intergeodesics on Q and searching for a permutation matrix that would take all points from S into Q. And in fact, the first time that it was written this way was, I think, by Anastasia Dubrovina. And we tried at the time to work on it from a continuous point of view using some local convergence. I mean, we started from the multidimensional scaling as initial condition and then defined convex optimization problems in order to push the points into their local solutions so that they would minimize this functional. But this is, in a sense, what we would like to resolve. Now, together with Jonathan Aflalo, what Anastasia was doing was recoding the problem into a functional map-like problem, which means that distance functions are in essence smooth functions, okay? So if I take the intergeodesic distances and I project them into the Fourier that is defined on the surface, Fourier that is defined by the Laplace-Beltrami operator on the surface, then what I get is the following shape. And in fact, it can be captured by a low rank matrix alpha that would still capture the essence of these intergeodesic distances. The same can be done for the surface Q. Okay, and the question now is what happens about the permutation. And in fact, the permutation can also be written in the same manner. So if I have everything written in the Fourier domain, then I can write the problem equivalently in the Fourier domain and try to solve it in a more efficient way. Okay, and this is how the spectral, generalized, multidimensional scaling method was working. And again, this is, I would say, almost 7 years since we played with that. So we use multidimensional scaling, generalized with the Bronstein, spectral, geodesic distance descriptors, PCA, regular PCA, and various other ways that we threw on this problem. And then the question is, can you actually train a network in order to tackle the same problem? So to that end, I will go to functional maps. Functional maps by Osyanikov, Solomon, Gibas, Mirella Benchen, and I'm obviously forgetting somebody. By the way, each of the authors of this brilliant paper got a position in one of the best universities in the world. Max in École Polytechnique, Mirella at the Technion, Solomon in MIT. And I can say other jokes about it, but this is it. Okay, so what is the idea behind functional maps? You take your surface and you compute corresponding features for surface S and surface Y. So before it was S and Q, now it's X and Y. And you also compute, for example, the eigenfunctions from the Laplace-Beltrami operator of X and Y. And then you project the features onto the eigenfunctions and you get this matrix of numbers alpha. And you do the same for Y and you get this matrix of coefficients beta. And the permutation in the frequency domain is nothing but dividing alphas by betas. Okay, so you can get the permutation by just looking at the projection of corresponding features onto the corresponding Fourier harmonics. Now, you need corresponding features. For example, you need some rough nose detector and rough ear detector and rough eye detector if at the end of the day you would like to compare between to match faces. And this is not such an easy way to go, but still you can do that. So the question is, in neural network, we learned that you need to take the features and somehow replace them by a neural network. And the idea of Roy Litani, clever student of Alex Bronstein, Remes, Rodola, and Michael, was to split the features into 2 steps. First of all, what you do is you compute some sort of features, shot features, that define, for example, this is, you just inflate about each point a sphere, and you cut the number of sections of sphere that are cutting the surface, and this is how you compute this kind of a feature. Then, so for each and every point on the surface, you have a set of features. If it would have been 3, I would call it color, but say 300 numbers at each and every point on the surface. Then for each and every point, you use a neural network in order to blend these numbers so that they would best fit into the rest of the functional map concept. Okay, so again, the output is being projected, and this is the same network for the X and Y. So you train the network for many surfaces, and you need to know the correspondence between X and Y so that you would have some loss to optimize with respect. Okay, so this is called supervised learning. You need to know exactly which point in X belongs to which point in Y, and this is how you compute your loss, and you backpropagate and you optimize for the coefficients for the parameters of these 2 networks simultaneously. I mean, they are not Siamese because this is how the network would look like at the end, but this is what you're doing. Okay. Now, this is nice, but there are 2 cavities here. First of all, the fact that you need to compute features. These are specific features, and neural network are telling us that I need to get rid of features somehow. I mean, eigenfunctions is something that I can live with. This is something which is universal for each and every surface. But inflating spheres is something which is subjective in some sense. And the question is how to get rid of these guys, as well as the need to compute this penalty in a supervised manner. And the remedy came from Oshvi Halimi, who did the following idea. What she said is, look, let's go to the idea of Gromov-Hausdorff and let's compute the intergeodesics for X and for Y and optimize for this measure here at the end. So you don't need to know which point in X corresponds to which point in Y. In fact, you don't need to know the permutation because it is being fed through this pipe. All you need to do is optimize for the metric coefficients by using this penalty at the end. And she got results probably as good as the supervised, in some cases even better than the supervised one. And in fact, you could get two new shapes and optimize the network for any two given shapes and find the matching even for non-related objects. Okay, and the next problem is, can we actually get rid of these shots of these specific features in some way? It works. It works also for shapes with the holes. And now comes the new part. And obviously, it can work for large distortions, small distortions. And now comes the new part. So let me take you back into the fact that I have two ways of measuring length along a curve. Okay, the first one was Euclidean. The other one was scaling variant. And for surfaces, we can play the same trick. We can have a scaling variant metric and a regular metric, and can have scaling regular harmonics, Fouriers, and scaling variant ones. And we can, in fact, look at the interaction between these two eigenfunctions defined on the surface, and this would give us a discrete number, a matrix of numbers that would identify these two surfaces, okay? And just as a side note, I could tell you that the metric in the scaling variant case is nothing but taking the regular metric and multiplying it by the Gaussian curvature. Okay, so this is Gauss, this is Beltrami, and this is the Gaussian curvature. Okay, and this is Riemann here. Okay. So these are the eigenfunctions displayed as colors when you project them onto the surface that you've computed these eigenfunctions with respect to for the regular metric. And this is what happens with the scaling variant method. Okay, so you see that you have these two kind of frequencies that you have. Now, what Oshri first did is compute the same metric for this red horse. And then the interaction between these two, I mean, the inner product between these two definitions gave her a matrix, okay? And if you take this matrix for all these horses and all these ladies, you can see that they are fundamentally different between a horse and a lady, but they are very similar between the ladies and very similar between the horse. In fact, there is a small cheating here. I mean, eigenfunctions can be computed up to a sign, okay? So there is sign ambiguity. In fact, if you also introduce small perturbations, then you may have flips of when the spectrum becomes non-simple. Okay, so there are some noises that you need to take care of when you do this projection, but still she could compare between shapes. Each point here represents a horse in a different pose, each point here represents a human in a different pose, etc. And you can take people and try to split between them. And it worked pretty well. The question is, how can you push it further? And the idea, I see that I'm short in time, so the idea in a nutshell was the following. So just to remind you where we stopped before. Before we stopped at the following point, we had this Halimi trick of taking the final measure of comparing between the distances in X and Y and replacing it with the permutation of the intergeodesics of Y into those of X. Okay, so you optimize for P and you backpropagate and you optimize for the coefficients for the blending of the shot here. Now, remember that we wanted to get rid of all this short idea. I mean, can we actually do something about it without and still be within a learning methodology and without resorting to how do they call it? Manually designed features. Okay, so it's manually designed features. And the answer by Amit Bracha was actually very interesting. The idea is rather than fitting the eigenfunctions here and features here, let's fit here the eigenfunctions with respect to a different metric. So in this channel, we would still pipe the same eigenfunctions, I mean the harmonics. And here we would feed the harmonics with respect to a different metric, okay? And again, I know I'm aware of the fact that in Paris, some people are now working in the last 2 years of asking the question, what would be the best space in which to apply this functional map idea? But bear with me to this line of thought, maybe you'd like it as well. So again, what Amit did is the following. Using the functional map idea, he was still keeping the functional map framework and this unsupervised idea. But rather than feeding features, what he did is fed the scale invariant eigenfunctions into something, okay, into something that he's training. Now, what is this something? Remember that if I would like to ask what would be the relation between x and y, or actually the eigenfunction, the scale invariant eigenfunction between x and y, there should be something very similar to a rotation matrix that, now rotation in the large sense, you can also flip the sign of the eigenfunctions so that you would be able to match the phi and the psi's tilde in the best possible way. So what Amit was doing was optimizing for a rotation matrix, and the rotation matrix was actually had a support that looks like that. It's a funnel shape. It's basically a unitary matrix with a funnel shape support. So optimizing for a small number of this R, he was able to match the eigenfunctions, the scale invariant eigenfunction of x to the scale invariant eigenfunctions of y. And then obviously the matching between the shapes becomes trivial, becomes almost immediate using the functional map framework. So it's not a neural network. Why is it not a neural network? I mean, we have everything here. We have the backpropagation idea and we train for R, but we train for R for each and every 2 shapes. So for each and every 2 shapes, we do the backpropagation and we look for the rotation matrix that would fit psi tilde to phi tilde. But then we cannot reuse it for the next 2 shapes because we need to compute the whole story from the beginning. So this is just to show you that if before I have these 2 isometric shapes and the corresponding eigenfunctions did not correspond to one another, after the rotation they did. Okay, so you can see that again, before and after this rotation, there is the eigenfunctions were matched. And again, you can show it for many poses and many shapes. And you can see that again, before these 2 eigenfunctions are not completely, but almost completely different. And again, after the matching, you can find them almost to be identical. This is more or less it. I'll be happy to answer any question that you may have. And thank you again for your attention. And I would say that next time, I would really like to be physically embedded in Paris for a talk.
Thank you very much, Ronnie, for this impressive talk. And yeah, of course, I hope to see you in real next time. But so first, are there any questions? For those who don't know about it, what you see on the slide now is the parking lot of Technion that was decorated by Ronnie's talent.
Yeah, and my daughter. Yeah, and my daughter.
Okay, so anybody else for questions? I saw a hand.
So you can raise your hand, or you can write on the chat if you don't want to open your mic, or just open your mic. I think you have the ability to open your mic if you do have questions.
In the meantime, maybe I will ask something. So next week at the ICCV conference, there will be a panel about old school, new school panel about deep learning versus classical methods in computer vision. So in your work, you've been working on what you could call classical method, as well as learning or deep learning. And what would be your position about that? Would you have any comment to say one versus the other?
So again, if you are asking me what is more important, then it doesn't matter. I mean, all of my students now, the first thing that they are doing is running deep learning. In deep learning, you don't need to understand much in order for things to do okay. But if you'd like to excel, you need some tricks and tweaks in order to be better than the rest. And I think that if you learn geometry, variational methods, all the fundamentals in mathematics, you can do much better than the rest of the competitors. And I've seen it in many cases. I mean, I've seen it in I was for a decade in Intel, and I've seen it again. And if you look, I was working with Intel group that is doing face recognition, and there is this Grand Challenge face recognition vendor test, and they rank you according to how you are with respect of the rest of the competitors. So Intel started, I think, at being at the 300th place, and then they called me, and we propagated into the 20th. I mean, now we are at the top tier somehow, top 30 or something like that. And the question was, in most cases, was how to generate. I mean, how you accumulate data. And this is a fundamental question. I would say in many cases it is much more important than the architecture that you're using or the loss you're using. I mean, the loss is important, obviously, but the fundamental idea is how you accumulate or generate a lot of data, which is relevant. And generating this data is a huge problem. And what we did is we built a synthesizer, and with the synthesizer, we could compensate for projective transformations. And I mean, if you're looking at the telephone, then when you put it close to your face, then you need to compensate the lighting, different lighting conditions. Over there, you can do whatever you want. So you need to have a simulator. And this is how you jump from the last tier to the top tier. Yeah, Gabriel.
Yeah, so I was wondering regarding the deep Gromov-Hausdorff type approaches. It's a general idea that like these questions are like NP-hard, and we want to use deep network to find ways to solve NP-hard problem, or is it rather like just the original question, like even the Gromov-Hausdorff question is not the good one, and we'll train a neural net to find some better question or better formulation?
Well, if you can use neural network to find a better question, then this could be great. I mean, but again, I haven't seen neural networks giving you questions. I mean, they could give you answers, but I doubt it if they could give you questions. Now, you are right about the fact that if you're looking at comparing two shapes from a Gromov-Hausdorff perspective, this is an NP-hard problem. But in shapes, you have the smoothness that you have. You don't just have an arbitrary topological space. You don't have order between the points, but you know which point is close to the other. And this is why projecting the problem into the spectral domain and working in a low-dimensional space is allowing this intrinsically very different problem to become solvable. So this is one way of reducing your number of parameters from basically exponential infinity to something which is bearable. Obviously, you don't solve the original problem. I mean, the original probabilistic problem as is, but rather relax it into something which you can handle. So again, the functional map idea is a beautiful idea because it tells you, rather than working with this large probabilistic problem, just reduce it into something, assuming that your surfaces are smooth and you can work in a low-dimensional space, then do it in this space. Afterwards, you can refine it using the Gromov-Hausdorff, I mean, some local version, local convex version of relaxing the Gromov-Hausdorff. But again, it's only after you land onto some significant Bayesian of attraction.
And are you aware of theoretical results that would prove that at the end of the day, with this type of relaxation, this would actually be tight and you would somehow solve the original NP hard problem, or is it like rather like experimentally?
Well, no. You don't solve the NP. Again, to the best of my knowledge, maybe you could.
No, but it could be true. It could be true. It could be true that for some smooth shapes, the problem is not NP hard. And,
oh, for smooth shapes, definitely. But I don't know of any proof like that. I'll be happy to learn if you know.
No, I don't know. So I'm looking also for,
This
for
could
progress
be
in this direction. Like some constraint on the shape that would make that the problem is actually solvable and that we could prove that.
No, I'm not familiar with such proofs, and I'll be really interested to see if you limit your space of surfaces, you can have something like that.
Okay, thanks. A great talk, by the way.
Thank you.
Always a pleasure.
Thank you.
Bonjour Albert.
Oui, salut Laurent. Hi, Ron.
Albert.
Yeah,
Albert.
Hi. Can you hear me?
Yeah, sure.
Okay.
Just
my question was, I didn't catch exactly in what sense you meant that the Fourier functions were optimal. That you mentioned that exactly in what sense you were meaning that. And so in the example that you showed, like the shark or other things, the curvature has very strong spikes because you have corner a little everywhere. So then, okay, do you, in a way, why do you want to use Fourier? Don't you have in mind other representation for lowering the dimensionality? Okay, maybe I missed your point, but
no. I understand. I think that I understand the question. So first of all, about the Fourier, this is in the usual sense. If you know that your functions have Dirichlet bounded Dirichlet energy,
okay,
and this is the only thing that you know, and you have just a k number of functions in order to represent your given set of these functions.
It's the best.
The Fourier is optimal because what you do is you take the transpose operator times the operator and you decompose it, and what you get is the Fourier.
So this is based on the model that you take for your shape. Okay.
Yeah, and it also applies to surfaces. I mean, it is not limited to a one-dimensional case. It would apply to any dimensional space that you'd like. I mean, you can take two-dimensional manifolds, three-dimensional manifolds, and then it would. In fact, we started from two-dimensional manifold, and then we reduced everything to a one-dimensional case, in which I know that wavelets are the optimal way of dealing with discontinuities. But again, we started from two-dimensional manifolds and then migrated to one-dimensional manifolds in order to understand what is going on. And I know that if you have discontinuities of the curvature if you have this piecewise constant or piecewise smooth functions, then there are better ways of representing your functions in these domains. I hope I answered the question.
Yeah, sure. Because on your examples, on your what you display, it looked like you had such things.
We did. Yeah, I did. And again, if you think about it more, then representing a permutation matrix in a Fourier space is probably the worst thing that you can do. Okay, and this is what the functional map idea is doing. But you get a smooth version of the permutation matrix, something like, and then you can think about it as mapping between probabilities, and it's not exactly a permutation, but rather some smooth version of the permutation. But the power of reducing this problem into this low-dimensional space that is solvable is what makes the magic, is what allows us to do something with this problem.
Okay. And I actually agree with the comment of Gabriel before. Okay, thank you very much. Nice talk, and hope to see you in person sometimes. Bye.
Same.
So, any other question? So Ronnie, you've been working a lot on face recognition, providing very efficient algorithms. So what about face recognition with a mask? Did you do anything on, do things that you need to?
So I can tell you that the moment the business unit tells you that this is what you have to do. So again, the group in Intel had an application that works with a mask. Obviously, the recognition rates goes down and the false acceptance goes up. I mean, it obviously distorts something, but if you just like to get to enter your phone, you can do that with a mask or with sunglasses that usually don't work for others. So what they did is they did two-level recognition, authentication. The first one is getting into your telephone, and the next one would be to get into your bank. So in order to get into your bank account, you need to take the mask off. But the first one, I wouldn't tell you to shave, but at least taking the mask off. But at the second level, you need to be more sensitive to what you're looking at. But the results that we were getting were quite amazing. I was amazed by how efficient these networks. And by the way, the time it took us to develop this system was amazingly fast. Usually it takes 2 years to have something that I mean, without networks, it used to take us about 2 years to have some stable product that you can show. With this one, after 6 months, you had something that was actually working.
Okay. So anybody want to ask a question or in the discussion? Or
Gautam, I see you in the audience.
Hi, Ronnie. It was a great talk.
No. Questions?
No questions.
Anybody for questions? No?
This is after lunch, no, everybody.
Yeah, no question on Iconal solver. I would have loved people to. No, I'm kidding, but it's a great idea. I mean, it works great, right? Using deep learning for Iconal solver. Or...
Yep.
It seems to be something I should try.
Yeah, you know what we did is we just replaced the update scheme with a network, with a fully connected multi-layer network. Now, let me give you a challenge that I still don't know why.
No.
We could get to a second order accurate solver without much difficulty. I mean, just playing with the stuff. From some reason, we couldn't push it to third order accuracy. I don't know, again, and I have no idea why. It was probably a bug or something like that, but you need to obviously take a larger support, okay? Because in order to get to a third order approximation, you need to have your derivatives up to higher order. But the question is there any fundamental barrier that you cannot push it into a third order approximator? Or is it just because of a bug? So this is where you really need to be a mathematician in order to tackle this problem.
But you think it's just that the optimizer gets stuck somewhere and it doesn't, I mean, it cannot reach to the accuracy you would like, or it's?
Yeah, it was stuck at second order accuracy.
Yeah, but it's like a very non-convex optimization method to learn the...
You're right.
To learn the network.
So remember that at the end of the day, I'm giving it many examples that I cut from spheres and planes and cylinders. So, and cones. So at the end of the day, it sees almost all variations of surfaces. And the question is, do you actually capture all variations of surfaces, or do you have any analytic solution for local distances between more complicated scenarios that you can fit into the problem?
And maybe the meshes are too degenerate to be able to have even the existence of such a thing, unless the stencil goes crazy. I don't know.
Maybe.
I mean, maybe there is. Jean-Marie Mirbeau is the expert, so we should ask him the question if he can disprove or prove that if you have very bad meshes and very
no. Forget about bad meshes. Even training for good meshes. I mean, for
with good meshes.
for sphere lives. I mean, just random sample a sphere and show that if you just do refining of the sphere somehow, then you do converge to the in a third order rate. Even
okay,
there.
In this case, yeah, it's weird. Looks weird. Good question.
Okay. So, should we close the session, or anybody wants to ask?
So we can thank Ron virtually.
Okay. It was a virtual pleasure.
Yeah, for us also. There was a lot of people. So thanks. See you.